Welcome back again. This time what we're going to talk about is Snubber Diodes, decoupling capacitors, and H-bridges. Should be good. So we're going to start things off talking about Snubber Diodes, kind of why we need them, what they do, how we're going to actually use them. So let's start with the why. So in order to figure out the why, we're going to have to take a look at a motor and how we model a motor. So this diagram's kind of turned on in just so you can see how it works. So what this diagram represents is this is showing a power supply up here, admittedly drawn with a different symbol, but it's still like a power supply. So let's say it's a 12-volt supply. We have power that's going to be flowing through our motor and then into a transistor. And the transistor is going to control this thing, just like we talked about in previous days. So a microcontroller turning the transistor on and off. Electrically, how we model these things in the simplest way is just as a resistor. So there's some voltage at the top, let's say it's 12. There's some voltage at the bottom, let's say it's very near 0. And what this thing is, it has a set amount of current based on how many ohms the motor is. So we talk about like a 40 ohm motor and things like that. So that's the simple diagram, and that'll get you pretty far. But today we're going to look at the diagram a bit more in detail and figure out what problems come up because of it. So a better example, instead of just a resistor, is to add a couple more components. So these additional components are two things. One is an inductor. So an inductor is in a motor, and what it does is it kind of wants to keep current going, right? So if you instantly turn off current, so if you just turn it off, the inductor doesn't stop, right? So it keeps delivering current. So it's kind of the analogy of, there's actually a really good picture on the next slide. So here's the example for what an inductor looks like. Essentially, it's like a paddle wheel or something that kind of like has inertia and momentum. So if current is flowing through a wire and there's an inductor on it, it kind of takes a while to get going, but then once it gets going, it wants to stay going. And so that's kind of the idea of what an inductor is all about. So that's in the system. For a real motor, they all have some inductance to them. And then there's also a counter EMF. I'm not as worried about that today. That's basically saying that explains how generators work, right? So if you drive the shaft, like with gas power or something, you turn it with your hands, it does create a voltage. I'm not as worried about that. The main one I'm worried about today is this inductor and how do we handle what's called inductive kick. So the problem is, if you were to do an experiment with this, you would drive this thing, it would be on, life would be good, and then if you were to turn it on and off rapidly or just turn it off, this shows turning it on and off at 50 hertz. As soon as you turn it off, that inductor is not happy, right? Because it wants to keep flowing current, but there's nowhere for it to go because the transistor just got turned off. So what happens here is you have a voltage spike. So the voltage up here starts to get really high. It does eventually dissipate, like it will go somewhere, probably not somewhere you would like. It creates noise in the power line primarily. But there's this pressure that builds up at this location that you really want to do something about. So that's where decoupling capacitors need to come into play. So with no decoupling capacitor in this experiment, these numbers are hard to read, but this spike actually hit 233 volts, right? And so 233 volts is just like a little spark that just kind of shoots through the system and has the potential to cause damage. So, there was at 0, here was at 12, but there was this spike, which was bad. So where you put a diode to help prevent this problem is in the same spots as where the motor connects. So these inductor and resistor represent our motor. If we put a diode in those same locations, we put it with its bar pointing towards power. What will happen is this spot, it'll want to climb to like 233 volts. And so way before then we want to do something, right? Well, this spot is at 12 volts, and as soon as this spot gets to be one diode drop higher, let's say this diode is a 0.7 forward voltage drop diode, then when this spot gets to 12.7, then what's going to happen is current's going to start to flow. So it's a release valve, right? So when that voltage starts to go higher and higher and higher, instead of like letting it get out of control, as soon as it gets up to like 0.7, then things shut down. The other nice thing about it is that it doesn't cause any problems while the circuit is on. So while the circuit is on, current chooses to go that way, and you won't see any current flowing this way, because that would be flowing in the opposite direction of the diode. So they're really handy in that they stay out of your way until you need them. Just to kind of finish with our experiment, if you were to run this same experiment that before hit 233, again with the diode in place, what will happen is it'll start to skyrocket, but then when it gets to one diode drop above the voltage supply level, so if this was 12 and this is 12.7, say, then it will shut off, and it will give a happy path, a happy controlled path for that voltage to go. So that's the idea, pretty simple. Seeing what these things look like in reality, how you use them. They're always drawn with a simple little triangle and bar. Note that if it was a light emitting diode, so an LED, typically people draw it with a circle around there. If you leave off the circle, then it's just a plain old diode. The plain old diodes that we actually have, they look like this. Their legs are anode and cathode, just like an LED, right? Honestly, the only difference between a diode and a light emitting is diodes don't emit light. Pretty simple. They also are a little bit more robust, and their forward voltage is typically more like 0.7 instead of like 1.7. So it's a lower forward voltage drop. The way you can remember when you actually need one is there's always a bar on the actual device. That bar is the bar that you see in the diagram. Oops, my arrow kind of stunk there. The bar that you see in the diagram. So that'll tell you how to plug them in. So this end will always go to power, and then this end will go to the other end of the motor. And if you think about it, those are the same places the motor gets plugged in at, right? So it goes like that. And then down here you'll have your, your transistor, which will go to ground. So that's kind of the idea. Just to mention one more thing about snubber diodes. We mentioned this yesterday when we talked about Darlingtons. Darlingtons actually have a snubber diode built in, which makes them even easier to use. The only thing that you need to do on a Darlington is this line right here, which is sometimes labeled COM, which confuses me, needs to be connected to whatever is powering your load. So whatever is powering your load, you put that line in there as well. All of a sudden you've got snubber diodes for free. And it works out that your load connects here, your load connects there. Internally, this is connected to where your load is connected, and then you just need to connect the other end to whatever powers your load. So that's kind of it on snubber diodes. Hopefully you see why they're an advantage. They control this out-of-control voltage, and they're pretty easy to use. So it's something we're going to add to help protect our microcontrollers from our inductive kick from our motors. This is kind of phase one protection. See you next time where we talk about another type of protection.